Hey class, we're going to cover today chapter 3. We're going to go into section 3.2 of our notes. And so what that looks like is the electron model. So we've already covered all these experiments. We already covered the idea of how we got to the idea that there's a dense center called the nucleus. And now we're going to kind of talk more about the atom in general and realize that the atom is just mostly empty space. There we go. So now we're at the electron cloud model. So this is a current model we work off of. It currently, again, has the idea that in the center of our atom is this dense area that has a positive charge. Well, why is it a positive charge? Because it is full of protons and neutrons the neutrons have no charge. But around it is this electron cloud. Now, when we say electron cloud, we're just trying to use human words to describe and to explain what's going on the atomic level. And so we use words like electron cloud or the electron field or the electron shells. You even hear things like the electron rings or the electron orbitals. All these are words to try to help you understand and help teachers explain what is going on and what are the different characteristics that these electrons have and where they exist. So when we say electron cloud, first of all, notice that we know a good amount about electrons, but we don't know everything. And electrons are really finicky, really interesting little particles that we have in this world. There's a guy named, there's a principle called the Heisenberg uncertainty principle. And what it talks about is that as an electron, we can kind of know where it's at, but we can't know anything else about it. Or we can find the momentum of it, the energy an electron has, but we can't locate where it's at. Or we can know about the time it was in a location, but we can't know anything else. And so there's this weirdness about electrons that we know they exist somewhere, but we can only find one fact about them at one time. And it's kind of cool. It's all in quantum mechanics. And basically it comes down to the idea right now that we believe electrons teleport. So we used to think that electrons just orbited the nucleus, kind of like our planet orbits the sun. And for us, we can measure the speed and the location and the time that our Earth has at any given point in time. Well, however, when you get into the nucleus and the electrons, for some reason, the electron would appear here, and then the next second it would appear here. Then the next second it would appear here, and then the next second it would appear here. And so whatever's going on, we understand the electron has a probability about where it would exist, but we can't know the exact time, location, energy, all at the same time. We can only use one. And there's a guy named Schrodinger. He writes about this with a cat, and he says that imagine you got a cat inside a box, and you can hear the cat, and you know he's in there, but the moment you open up the door to look at the cat or take the lid off the box to see the cat, there's a bomb that goes off, and the cat explodes and dies. So you can know and you can figure out certain things about the cat, but the moment you actually look inside, you cannot see where he's at anymore. You can only see where he was at a second ago. And again, it comes this idea that electrons move around in such a weird way that we don't understand. It has to do with the way they travel in a wave function. But it's really cool stuff. But basically, it comes down to the idea that electrons might be able to teleport. And if electrons are just pieces of matter and they can teleport from one location to another location instantly, what's to say humans can't teleport someday? So as we move on, we're just talking about, again, this idea of an atom. We've already seen, if you already read, about how an atom, if it was the size of a football stadium, think about Nippert for UC Bearcats, or Paul Brown for the Bengals, or the Great American Ballpark, or Ross Aid at Purdue. Think about a stadium, and if you think about the idea of a dime in the middle of that stadium, that would give you an idea as to the size of an atom and how much space is in there. So if the atom is a football stadium, a dime in the center on the 50-yard line would be your nucleus. And if you look at the I on the dime for Roosevelt, that would be the same size as an electron. And what we see here is that atoms are just mostly empty spaces. So what are atoms made of? Well, we know they're made of protons that have a positive charge. And we know that charge is equal, yet opposite to the charge of an electron. So with that being said, if atoms are neutral, if there's no charge in atoms, the number of protons has to equal the number of electrons. Again, when an atom is neutral, the number of protons has to equal the number of electrons. And so we also know that our protons and our neutrons have roughly the same mass. And we talked about a couple days ago that an electron is 1,836 times smaller than that of a positive proton. And so all this does is just gives us an accurate picture, or not accurate, but a more clear picture of what's going on inside the atom. And we see that the nucleus has the majority of the mass that comes from the protons and the neutrons. And you think about that. If a proton is a positive charge and an electron is a negative charge, those charges cancel each other out because they're equal yet opposite charges. And we use the term positive and negative just to clarify direction or the magnitude of what they are, but they're equal and opposite. But what's really neat is that if a proton is 2,000 times bigger than an electron, wouldn't you expect it to have more of a charge? We don't find that. We see they have equal yet opposite charges, even though the protons carry all the mass. And so then you go back and you just think about how that mass or that density of the nucleus just exponentially gets bigger. Because if I have a hydrogen with one proton and I have an electron in that hydrogen, that means this dense nucleus is 2,000 times bigger than my area where the electron is, than the area of the rest of the football stadium. But let's think about a helium atom. An atom of helium has two protons and 2 neutrons, so it has an atomic mass of 4. But yet, it's going to have 2 electrons still that orbit around, that move around that center of that atom. And so when you think about that, that means there's going to be 8,000 times the mass here in the center of my nucleus as that in the rest of the electron shell, and the rest of the atom. So it's kind of crazy when we exponentially get bigger, or when we get bigger with our atomic number and our atomic masses, the mass and the density of the nucleus gets exponentially bigger than that of the surrounding area and the surrounding shells. So now let's consider the center of an atom where the nucleus exists. We've already learned that like forces repel each other. So if I have 2 magnets with the same poles facing each other, there's going to be a repulsion here. So think about the nucleus. Inside the nucleus, we said was just protons. And if every proton has a positive charge and they have the neutrons with no charge, how do they stay so tightly close together? How are they so packed tight together? There has to be some other force that are keeping those protons together, because we've already learned that left alone by their own charges, they would push away from each other. And so that's where we come into the idea of what we call nuclear forces, which are just some short-range forces that hold all of our nucleus together. And here you can see this right here would refer to a lithium-6 isotope, 3 protons and 3 neutrons, which we'll talk about more isotopes in my next video. And so wrapping up, we're going to talk about this more. I'll make another video of how we get to understand what side of the atom. So get your periodic tables out, and we'll come back and pick up here. Thanks.